Hello everyone, welcome to this lecture. I am Udom Philemon of Nubira Process Designer. Now, in our last lecture, we were looking at heterogeneous catalysis, simulating the heterogeneous catalytic model using Aspen Hysys. So this will be a continuation of that particular lecture. Now, in this lecture, we will be putting into consideration void fraction or bed voidage. Now, void fraction is the amount of space that is available for the flow of fluids, right? So now, in our process that we simulated last time, we did not specify bed voidage, right? Let's see. Okay, yeah, so the void fraction was 1, right? So this 1 here signifies that the whole volume of the reactor is available for fluid flow, and that means, or it automatically signifies, that there is no catalyst in the reactor, right? So whenever you are adding catalyst to your reactor, you have to factor in bed voidage. Now, if we go to the reaction section, right here, you see it says in the catalyst data, it says void fraction is specified as 1, no catalyst information is needed, right? So that means when your void fraction is 1, it means there is no catalyst in your reactor, right? So when there is catalyst in your reactor, then your void fraction cannot be 1, right? Though void fraction ranges from 0 to 1, right? Void fraction ranges from 0 to 1, but when it's specified as 1, you cannot specify catalyst information, right? So when you are dealing with heterogeneous catalysis, which involves the use of catalysts, you would have to specify void fraction, right? Now, in a case where you are using the Ergon equation, you may not be able to alter your bed voidage value. Now, if you go back to rating and you try to change the value to, say, 0.4, for example. Now, if you change it to 0.4, that's a fraction, right? Your reactor will not solve, because it is in it was specified as Ergon equation, right? The only time you can alter your void fraction value is when you specify it as user specified. So when you specify it as user specified, which will now require you to specify your change in pressure, that is when your simulation will solve, and that is when you can also alter the bed voidage. So if you specify this as 0, you see your simulation will solve, right? Now if you go back there, if you go back to rating, you are able to alter your bed voidage now. So whenever you want to specify void fraction, the first step is to go to design, go to parameters, and click on user specified for pressure drop parameters, right? Click on user specified, then you specify your pressure drop, right? Then you can now specify your void fraction, and then your PFR will solve, right? So that's it. Now, if you still change it back to Ergon equation, you will see that it will no longer solve, right? So it has to always be in user specified for you to be able to specify your void fraction. Okay, so that's it. Now that the void fraction is no longer 1, we can now make changes to the catalyst data, right? We can make changes to the catalyst data when the void fraction is not 1. So now you can specify particle diameter, particle sphericity, solid density, bulk density, solid heat capacity, right, based on the data you have. Now you would also note that this specification of bed voidage also it has an effect on the composition, the product composition, right? So at bed voidage of 0.2 we have this composition. You see the composition of the product is very, very low because we reduced the bed voidage from 0 to 1. Okay, let's check the initial bed voidage when it was. Let's check the initial composition when the bed voidage was 1. Let me open this. So this is our initial simulation from the last tutorial, and we have our void fraction as 1, and then this was our composition. So for CO2 you have 0.0059. Then for HCl you have CO2 you have 0.0059. For HCl you have 0.0176. Let me confirm something from our reaction. Okay, so CO2 and HCl are our products. So you can see their composition. You see their composition 0.0059, 0.0176 at a void fraction of 1. Now if you go back to the other one we were working with before we came here, yes, this one. Now you see at 0.2 bed voidage you have 0.0009 and 0.0026. 0.0009, 0.0026 for CO2 and HCl. So the bed voidage has an effect on the product composition, the composition of the output. Now for this particular simulation we were solving, our bed voidage is supposed to be 0.5, so we can quickly specify that. Yes, so it's 0.5 instead. Yes, so this means that half of the total volume is available for fluid flow in the reactor. So now if you check the composition, see it has increased slightly as we changed it from 0.2 to 0.5, right? So now that we have a reactor which includes bed voidage and then catalyst specification, you may want to optimize some of the process conditions, right, in order to increase the output. So we'll be doing a few case studies to see if we can increase the product composition. Now we can work with temperature, pressure, then we can also work with reactor volume as well. So for reactor volume, I'll specify reactor volume here 2.28E3. okay, so I'll specify 2.28E minus 3. yes, so that I can be able to make use of it in the case study. I want to make use of reactor volume. So we'll go to our case study and do sensitivity analysis. Let's say add. So for case study 1, we are going to use the reactor temperature. Okay, no, let's use feed temperature. Done, is at 100. Then we'll be using let me see, we can use conversion. We can use the PFR conversion. So done. So we have this. Then we can run our setup. Current value is 100. Start value can be, okay, start value can still be 100. Then end will be, let's say, 1000. Then number of steps will be 20. Okay, I need to change this first to, I want to use sensitivity to just input it again. 1020 steps. Okay, so we are good. Now we can run it. Okay, so we have success. We have success for this particular case study. So we can check the results. You have the results here. So from what you can see, as temperature increases, the conversion increases as well. You can confirm that from the plots. Okay, so this is the plot for this particular, let me collapse all this, auto hide. Yes, so this is your plot for this particular case study 1, which is temperature or conversion against temperature. So as the temperature increases, the conversion increases as well. Then let's do another case study. Case study, add. Let's do for pressure, for feed pressure, feed pressure, feed pressure, feed pressure. We can still use conversion, actual percent conversion. Then our case study setup is selectivity. So you can do selectivity analysis with Aspen Hysys. Then we have 100 kPa to 1000 kPa. Then we have step size of 20. Yes, that's it. So we can run as well. Okay, so we have success. You can also check the results. Okay, from what I'm seeing here, an increase in pressure leads to a decrease in conversion. So yes, an increase in pressure leads to a decrease in conversion. So it means you may not want to increase pressure in this case. You may just leave it the way it is. You leave your pressure like that, because increasing it will only decrease the conversion, actual percent conversion. So what else? While temperature actually has a good effect, a very substantial effect on conversion, pressure doesn't, and rather it decreases it. Okay, so let's do for reactor volume. Let's do a case study for reactor volume. Reactor volume is reactor volume, add, let's see, find variables, reactor volume. Okay, I will also do one for bed voidage as well. I just saw bed voidage there. We have reactor volume. Let's enter reactor volume. Then find variables. We'll still use actual percent conversion. Okay, so for actual percent conversion, let me see. Click here. Yes. then enter, then click done. Case study, let me check. 1 and 2 are selectivity, right? Case study, yes. So these two will be selectivity. You can choose whatever you like, any of them, depending on what you want. Selectivity, nested, discrete, or base and shift. Okay, now for reactor volume, I'll use 0.5 E minus 3. 0.5 E minus 3, then let's say 1 meter cube. Enter. The number of steps size is just 20. I don't want it to be too much. Then I can run it. Okay, and success is, let me see, volume seems to not have so much effect on the conversion, right? It just has a slight increase at the beginning, then it's now constant from around 0.046 meter cube, which you can confirm from the table, from around 0.10. Let me see, but it actually starts from, yes, reactor volume at 99.99 conversion, you have 0.057 meter cube, right? So with this we can actually help to boost our product composition, right? So we can just pick some of these values. For example, we can pick this 0.05448 as our volume here, 0.05448, right? Then we can go back and choose from the plots. Okay, for pressure we are going to leave it at 100 because 100 seems to be optimized, right? 100 is optimized, it has the highest conversion, or actually it's 147, but we can leave it at 100. 100 is reasonable. Then for this one we can change the temperature. We can change it to say let's change it to 800. Let's use 800, though there are higher conversions for higher temperatures, but let's just use 800 for the feed. For the feed temperature, we change it to 800. Okay, before we change it, let's see what is there already at 100. Now at 100 you have, let's see the composition. You have 0.25 and 0.75 HCl, 0.25 CO2. Now if you change it to 800, what are we going to have? We change this to 800. Or really not solved? Why is it not solved? Let's see. So I specified 800 degrees Celsius, but it didn't solve. I checked the message and it says reaction temperature in PFR 100 exceeds the temperature specified in reaction, or one of the reactions in reaction set. So I decided to use a lower temperature like 500, and then it would still solve. So now I noticed something in the composition. The composition does not change, right? It doesn't change even if you use, let's go back, even if you use 100, it will still not change. it will still not change, and that is because the reactor volume has the highest effect on the product composition, right? Let's go back to our case studies. Now we have case study 1. This is case study 1, right? Temperature gives you a max conversion of 64. Case study 2 is pressure decreases the conversion. Case study 3 is reactor volume, right? Conversion versus reactor volume. Now this particular case study gives you the highest effect on conversion, which affects the product composition, right? So in this conversion now for the reactor volume, you notice that at that particular reactor volume specified, let's check it, at the particular reactor volume specified, which is 5.448 e raised to power minus 2, you have, I think, 99.99% conversion, right? So this actually has the highest effect among these parameters we have studied in our case study. It has the highest effect on conversion. So whatever temperature you are changing to will not even have an effect, right? Because the reactor volume has a higher effect on the conversion. It gives you a higher conversion than the temperature. So we can actually leave our temperature at that initial value, which is 100 degrees Celsius, and just play around with the reactor volume, which has the highest effect on conversion in this case, right? So in this case, it's actually reactor volume. So you see how this case study can actually help us determine which parameters are actually key in our process, which parameters have the major effect in the particular process we are trying to simulate. Now in other processes, it may not be reactor volume, it can be pressure or temperature or any other parameter. So this case study will help you to determine which parameters to focus on and then optimize in order to get good results, right? So at this point, we have come to the end of this video. In this video, we try to explain the importance of the void fraction or bed voidage and how it affects the catalyst specifications, right? And then we also try to optimize our process, right, to get good results. I hope you have gained some knowledge today. If you have further questions on what we have learned today, or even what we learned in the last tutorial, which was the introduction to the heterogeneous catalytic model, you could send in your comments. Then like this video, share to others, and subscribe to this channel for more information about process simulation. Thank you and have a good day.